Okay, so this is the 14.4 notes for stat honors. In this section, we're going to be dealing with yet again another measure that helps us with our regression procedures. This measure is going to be called correlation. I'm sure in your regular English language you've heard the word correlate before. So that's where you're going to be learning much more detail about that here. So note, this is indeed a linear correlation we're talking about, but we don't always use the linear word. That doesn't mean that you have to remember that it is actual linear. The more formal term for it is correlation coefficient. So students often confuse this with the coefficient of determination, which you learned in the last section because of this word here. So just get that all straightened out. But normally I just use the word correlation. What does it measure? This correlation, it measures the strength and direction of the linear relationship between two variables. Okay, so how does it do that? Well, let's look at these bullets. First, r can fall anywhere between -1 and 1. So remember, r squared could fall anywhere between 0 and 1, so r can fall anywhere between -1 and 1. So yes, r could be negative. The magnitude of r represents the strength of the relationship. So what does that mean? Basically, if you get any values that are near -1 or 1, that means a strong relationship, and the sign matters. So if you get a value near -1, then you have a strong negative correlation. What does that mean? Well, you understand what strong means. What is a negative correlation? Essentially, it's the same as slope in a sense, where a negative correlation basically means that as x increases, y decreases. So it's the same concept as slope. If you get a correlation near +1, then you have a strong positive correlation, but as x is increasing, y is increasing itself. So some of the things to take note of here is that the slope and r are going to have the same sign, SIGN, the same sign. So this can be useful later on when we do some calculations, which we'll talk about. But generally, correlation and slope will always have the same sign, which will help you in some of the things that you do. Now, one small thing, so we talked about strong relationships, but weak relationships are going to fall in the middle. So what number is dead center between -1 and 1? 0. And it makes sense, 0, something near 0 will have very little relationship. So that is the best way to determine and how to interpret types of correlations. Okay, so just for visual help, let's take a look at some graphs and how they're interpreted. So if you look at the first graph right here, it appears that we have a bunch of points that are pretty much on top of the regression line. And a matter of fact, in this example, they are all on the regression line. Now, this is very rare. It's almost impossible for this to happen. But if this did happen, then the correlation would be r equals exactly 1. Now, note, it's +1 because we are rising from left to right. In other words, the slope would be positive. So we have a +1. Now, if you look at the next problem, we have similar, but the points are a little bit more scattered, but they're really close to the line. So this is an example of a correlation of 0.9, which means still a very strong linear correlation, which is positive because it's rising left to right. If you go more scattered, so if you look at this example, you'll see the points are pretty scattered about, right? But there is some type of they are about the line, even though it looks like we're going to have, it turns out we're going to get 0.4 as r. So note, it is a positive, the points are still rising from left to right, but it looks like the scatter makes this a very weak positive correlation. Moving on, so sort of the opposite of this one. Let's say you had a falling line with all the points on the line. It would be a perfect negative linear correlation of r equals -1. Let's say we took the points and they're only a little bit about the line. It would be -0.9. Let's say we had points that were definitely in a falling direction as a whole, but they're pretty much scattered about. That would be a weak correlation. Now, what if we just had a bunch of points with no pattern whatsoever? So I call it essentially a sneeze on a screen. So it's just a bunch of points all over the place. That means that you'll have a correlation very close to 0, and In other words, no linear correlation. So this is a good way to visualize what this will look like. And just to reiterate here, correlation coefficient determines both the strength and the direction of only a linear relationship between the two variables. Okay, so just like in the last section, you already know how, hopefully you remember, using linreg, just like we did in the last section, not only did you get r squared, but r was sitting right there for you. So you already know that you can calculate this, but again, where does it come from? It's very important as a stats student that you know where you actually got these values from, even if you're going to be easily finding them on a calculator. So the formula for linear correlation coefficient is as follows. It's this R formula right here, where you do 1 over n minus 1 times the summation of x minus x bars times the y minus y bars, the product of them. And then that's going to be divided by sx over times sy. These are the sample standard deviations of all your x and y values. So this is not to be confused with these values that you calculated before. Nothing to do with that. These are instead simple standard deviations for each one of the data sets. So the key is how do we find these values? So what I'll do is I will go through the same exact example, the very simple example of these data points. Remember, with this graph and then the regression line that we calculated, that was y hat equals 1 plus x. We actually learned from r squared that this isn't a very good regression for predicting, but still it's a very useful example for doing our calculations. So if we go down to the formula chart here, if we look up here, what are the values that we actually need to know? Well, we're going to need to know this, right? So we can use a table to do that. We also know how to find standard deviation. So for example, look over here. This is actually the original standard deviation formula you learned a long time ago. And this is this is supposed to be a y, by the way. Change that. This is the standard deviation for y if we were to use a different variable for calculating the standard deviation. So if you look within those equations, if you went all the way back to the first couple chapters to find this equation, you'll see the sum of x minus x bar squared. So we need to find that. We also need to find the sum of y minus y bar squared. So we generate a table right here to compute all of those important things so we can find the correlation. Okay, so let's do that. So just to be clear, all I did was take these points and put them over here. So 1, 3, 2, 1, and 2, 5. X bar is clearly 2 if we took the average of these three, 1, 2, and 3. And if we took the average of 1, 3, and 5, we get 3 like we did in the last section. So x bar is 2 and y bar is 3. So we're going to take all the x's and subtract 2. So we're going to get negative 1, 0, and 1. We're going to take all the y's here and we're going to subtract 3. So we're going to get 0, negative 2, and 2. Okay, so what are the things that we have to compute for our calculations? The first thing, which is for our correlation numerator right here, is we need the product of these two columns. So what's the product? Well, if you look at negative 1 times 0, negative 1 times 0, we get 0. 0 times negative 2, we get 0. And 1 times 2, we get 2. Okay, so we get all those values of importance. I erased some things I didn't want to. 0, 2, and 2. So we get 0, 0, and 2. So according to this, we need the sum of that value, which is 2. What else do we need? We need x minus x bar squared. Why do we need that? Because that calculates the standard deviation of our x column. So, or that's part of the formula that calculates that. So what do? We have to take this column here and square it. So negative 1, 1, 0, 0, 1 squared is 1. The sum of that column is, again, 2. Last thing, in order to find the standard deviation of the y's, we need to find the sum of the y minus y bars, which is here. So therefore, we have to square this column. So we're going to get 0, 4, and 4. We've done some of this already, but it's valuable to see it live. If we add this column up, we get 8. Okay, so let's get rid of all this. I didn't mean to get rid of this right here. So what do we do next? So we have to take these numbers and we have to find the formula. So what is the standard deviation of x? It is equal to the square root of the sum of this column, so the sum of this column is right here, which is 2, over the sample size. Well, remember we have 3 data points, so 3 minus 1, and this will get you the square root of 1, which is 1. So the standard deviation of x is 1. What about the standard deviation of y? So we look at this and say, well, we need the square root of, we need this column, the sum, which was 8, over 3 minus 1. That's going to give me the square root of 4, which is 2. So the standard deviation of y is 2. We can then go to our initial formula for correlation, which is here, and we have all the variables that we need. So we go over here and say, okay, what is r equal to? It's equal to 1 over our n, which is 3 minus 1, times the sum of, don't write that, the sum of this, the product of this. Well, look at this. The sum is 2. So we're going to get, multiply by 2, over sx times sy, which is 1 times 2. Okay, what does that look like? Well, let me just shrink this. So that's going to be 1 over 3 minus 1 is, of course, a half. So we're doing a half of 2 over 1 times 2. That's going to give us 1/2, which is equal to 0.5. So we would say that our correlation is positive 0.5. Okay, so how do we interpret this value? So we know it's a positive linear relationship, which is verified by the fact that the slope of this line is rising. 0.5 is sort of a betweener, okay, number. So we would say, we could just use the word moderate. So we could say there's a moderate and positive linear relationship. So worth noting, there are some textbooks that actually give you a scale of how to determine, you know, what R is and how to say what's moderately strong, moderate weak. I'm not going to be too picky. If it's like 0.5, 0.6, you know, 0.7, kind of moderate. 0.8, 0.9, year 1, strong. If it's below 0.5, then you can just say weak. I guess that's the best way to really go about doing that. Okay, so let's return to the car example and the price, right? So over the last 3 sections and all of chapter 14, we've been basically filling out this chart. So we have our xy's, we have our x minus x bars, y minus y bars, we have the product of them, we have x minus x bar squared, y minus y bar squared. So we've been filling this out like crazy. There's no reason to return and do this again. So what I did was I brought all of the information back into one chart so we can use it to calculate the correlation coefficient for the car versus the price. So is the age and price based on this example a strong relationship or not? Well, let's find out how they're correlated. So remember, Sx is the equivalent of the square root of the sum of all the x minus x bar squared. So that is here. So the sum is 20.1819, so 20.1819 over n minus 1. Remember, there are 11 cars. So if we do this, we're going to get approximately 1.4206. So we'll keep that. This is SY again. I don't know. I had a cut-paste problem here. So make sure you change that. So again, we have to find the sum of the y minus y bars, which is now here. So we want this value. So that's going to be the square root of 9708.5456 over 11 minus 1, which is going to give us approximately 31.1585. Okay, that is, what am I going? Jesus, that's the sloppiest thing I've ever seen. 31.1585. All right. So using that, we can then go to our correlation just like we did before and calculate it. So 1 over 11 minus 1 to start, times the sum of the products, which is here, which is this number, right? So this number ended up being a negative in this standpoint. So we're going to get negative 408.9092. Okay, so note, I think it's important to realize here that this column is going to be really the important decider whether it's going to be a positive or negative correlation. So in the denominator, we can copy the answers that we got just above this for Sx and Sy. Okay, if we do all of this math, we're going to get negative 0.924 as our correlation. Okay, so what does this mean? So it's near negative 1, so definitely is strong, but this time we have a negative relationship. Strong and negative linear relationship. And this kind of makes sense just because the points were really stacked about the line when we originally did this. So and generally there's a strong relationship between age and the price of a car just in terms of real life. So it all kind of makes sense. Okay, so just remember that before we get to the last part here, in the calculator, you're making sure diagnostics is on. What I didn't, by the way, I didn't mention this in the previous slide. You do not have to turn diagnostics on every time. It's once you turn it on, it's always on unless you reset the calculator. I should have mentioned that in 14.3, but once you do linreg and number 8, you'll get R as well in your calculation, so you can then use that as your main sort of way to calculate correlation unless they specifically ask you to calculate it from scratch. So obviously the calculator and then knowing how to interpret it is really the key. Okay, some other things to point out. So here, so I'm not going to read it, but generally what's the relationship between R and R squared is exactly what you think they are, think it would be. If you have R, which is your correlation coefficient, all you need to do is square it, and you're going to get the coefficient of determination R squared. So it's no coincidence that one's R and one's R squared. So realize that. So it's very easy to find the coefficient of determination R squared if you're given the correlation coefficient. So realize that's easy. Feel free to do that. But just be careful though, because let's say you're given R squared, and which is a coefficient of determination, and they ask you to find the correlation. So if you, for example, let's say it's 0.853. Okay, so if you go, okay, I want to find R, so R is equal to the square root of 0.853. Here's the issue. When you take the square root of 0.853, you get a positive value if you're just doing it like in the sort of in your brain, I guess, like in the calculator. You're not thinking about the fact that R squared is always positive, but correlation could be positive or negative. So R would be equal to positive or negative square root of 0.853. So the only way to really determine whether it's positive or negative is to look at the graph. So when you look at the graph of these stack of points, if it's a rising line, then the correlation is positive. If it's a falling line, then the correlation will be negative. So this is actually important. I do recall on exam situations in the past, whether that'll be the same in this remote environment, that you will be asked to calculate R from R squared, and students will put the wrong answer and assume it is positive. Okay, so last thing here. This is essentially, I guess, the cautionary tail part of the lesson, which is our last page here, our last part of the page. I'm going to read these because they actually can be students can sort of muff these up a little bit and make minor errors in logic. So first one says, remember the correlation is a measure of just linear relationship between two variables. So if you try to use it on non-linear relationships, you're going to get misleading conclusions. So again, if you remember that picture I had, so if let's say you had like a bunch of points that are like this, and you did a linreg and you got this. So these points, even though this line has no place in being used as a regression line for these set of points, these points are closely packed about this line. So you actually might get a decent correlation, maybe like, let's just guess 0.65 from these calculations. But again, the calculations don't have eyes. They need human interaction to look at this and go, you should not be using correlation for this because correlation is meant for linear relationships. Okay, so next. The presence of outliers or influential observations can have a very impactful result, essentially. Why? Well, think about this for a second. Look at the formula for correlation. What is it using? X bar, Y bar. standard deviation, standard deviation. We know that these are non-resistant measures. You learned that all the way back at the beginning of the course. Why? Because if we put an outlier somewhere in there, the means and standard deviations will all be horribly affected. So that means if you're putting if you're putting 4 of these in one calculation, then the correlation is going to be an absolute debacle. So just realize that ideally we want to use correlation when outliers are not present in a data set. Okay, last thing, reading it. There are times where there might appear to be a strong linear relationship between 2 variables, but instead there could be a third variable, often called a lurking variable, causing both. Okay, so what does that mean exactly? So there's a lot of times where there might be a situation where you'll be looking at 2 variables and you'll say, oh, well, for instance, age of a car and its price. So we know that there's a strong correlation between the age of a car and the price. This is sort of proven over time. So we would say essentially that one causes the other to change. Sometimes you're going to get 2 variables where you'll find a correlation and everything's good. There's a pretty good relationship. But in reality, one variable is not causing the other. Instead, another variable is at play that's affecting this. So what's an example of that in this scenario? So let's say you run some type of analysis with 2 variables. One of the variables is ice cream sales, and another variable is dehydration ER visits. Okay, so we run a study and we find that there is an incredible high correlation between these 2 variables. So we would say, hey, there's a strong relationship between these 2 variables. But are we seriously going to say that ice cream sales is causing dehydration ER victims? Of course not. It's absolutely silly, and of course that's why I use this example, because it's out to lunch somewhere. So what's actually the lurking variable that's in play that is actually causing each of these to occur and create this relationship? Obviously, it's increase in temperature, right? Summer temperature, right? So what I'm getting at here is there's a very famous saying right here. It says correlation does not always imply causation. So you want to take great care whenever you're using correlation. So in a lot of cases it does. Correlation does imply some causation, but there are scenarios like this one where you have to be careful because ice cream sales is not causing dehydration ER visits to increase. Instead, temperature, which is a lurking variable, is causing both. So you just have to be careful with that. How do we deal with that, by the way, is with experimentation. We don't do a lot of experimentation in this class, really any of it. It is sometimes a part of stat classes, but you would have to take very strong, very clear experimentation protocols to limit your control variables. So if you remember placebo, you would have to do all of that kind of thing using placebos and avoiding the placebo effect, and that would help sort of create a causation or rule out other variables so that your correlation would be a causation.